This video is about electrostatics in materials that are conductors. First, we are going to review the basic properties of conductors with a focus on what the electric field does to a conductor and what the conductor does to the electric field. Let's start with what is the main characteristic of conductors. As you already know, we call conductors conductors because they can conduct electrical current, as opposed to insulators, where the electrons are stuck to stay around the atoms. Some electrons are free to move in a conductor. And that means that conductors have a very different response to electric field. So let's consider a uniform electric field. So here I'm showing the electric field lines. And now we put a conductor material inside this applied electric field. Electrons inside the conductor can move, so they will move in response to the electric field. The force on the electrons is QE, where Q is the charge of the electrons, so it's a negative charge. So the electrons are going to move left if the electric field is pointing right? And as a result, we will have excess minus charges on the left and excess positive charges on the right. But this charge distribution will result in an induced electric field, and this induced electric field comes from the induced surface charges, sigma induced. And so we know how to calculate the induced electric field in terms of sigma. Now, we don't need to do the calculation right now. The main thing is to realize that this electric field will point from the positive charges to the negative charges, so it will point in the opposite direction as the applied field. So if the applied field is pointing right, then the electrons move left, and the induced electric field is pointing left. And this process will happen really fast, and it will continue as long as the field inside is not zero. But eventually, the field inside will be zero, and the electrons inside will stop moving. So the first important property of a conductor is that the electric field inside a conductor is zero, even if there is an applied electric field outside. Now, since the electric field is zero, uniformly inside the conductor, then Gauss's law tells us that the charge density inside the conductor is also going to be zero. Now, of course, you have electrons and protons on the atoms, but on the scale of many atoms, right, the average charge density is going to be zero. The only non-neutral regions are on the surface. The charge inside a conductor is zero. Another consequence of the zero electric field inside the conductor is that the potential inside the conductor is going to be constant. Right? As you remember, in electrostatic, the difference in electric potential is given by minus the integral of E dl. So since E is zero everywhere inside, then the potential is the same everywhere inside. And finally, the last result that you need to know about is that the surface charges will also modify the electric field outside. So the shape of the electric field lines is going to be modified. There is one thing we can already know about the field lines. Previously, we have learned the boundary conditions for the E field, and we saw that the component of the field that is parallel to the surface, a surface of charges, this component is continuous across the surface. That is, E parallel outside is equal to E parallel inside. But since E inside is zero, that means the parallel component outside has to be zero as well. So the electric field only has a perpendicular component. That means the field lines terminate or start perpendicular to the surface of the conductor. And this figure here summarizes all the basic properties of conductors that you need to know in this lecture. The electric field inside is zero. The volume charge density inside is zero. The electric potential inside is uniform. And the field lines outside are bent so that they start or terminate perpendicular to the surface of the conductor. Now, there's another property that is a result of the induced charges. So let's say that you have a charge plus Q, and somewhere near this charge, we have a conductor. The charge plus Q creates an electric field, and that field will move the electrons inside the conductor. So we end up with minus charges moving towards the direction of the plus Q charge, and the opposite surface of the conductor will have positive charges. But now we have the plus Q charge and the minus surface that attract each other, and the plus Q charge and the positive surface that repel each other. And since the minus surface is closer to the charge than the positive surface, then the sum of these two forces is not going to cancel out, right? The attractive force will be larger. As a result, the plus Q charge will attract the conductor and vice versa. So in general, any charged body will attract conductors and vice versa. Now in chapter 3, we're going to calculate this force. And here I just give you the result, assuming that the conductor is a sphere of radius r and the plus Q charge is at a distance a from the center of the conductor, then the force is minus 1 over 4 pi epsilon naught Q square Ra over a square minus r square squared. Now the minus here is for attractive force, and you see that it goes as Q square, so it is attractive for positive or negative Q. And in homework 3, you will also find the induced surface charge. Now here's a question for you. Suppose that we have a neutral copper sphere and there is a cavity of some weird shape carved out of it. Now somewhere within the cavity there is a charge Q. What is the total charge on the outside surface of the copper sphere? So if you answer C, that the charge on the outer surface will be plus Q, then you're correct. Here is one way to find it. First, let's find the charge on the surface of the inside cavity. For this, draw a Gaussian surface in the copper that surrounds the cavity. What is the flux of E field crossing through this Gaussian surface? Right? The surface is in the copper, and the field inside a conductor is 0, so there is just no flux through the Gaussian surface. And so according to Gauss's law, that means that the total charge inside this Gaussian surface has to be 0. And since we already have a charge plus Q inside the cavity, it means that the charge on the inner surface has to be minus Q, so that the total is 0. Okay, but then the metal is neutral, so if we have minus Q on the inner surface, it means we must have plus Q on the outer surface. So the charge on the outer surface is plus Q, and it was answer C. Okay, you see that this does not depend on the position of the plus Q charge inside the cavity, and also this does not depend on the shape of the cavity. And we can go even further. How exactly are the charges going to distribute on the outer surface? The charges repel each other, so they will distribute uniformly on the outer surface. The field inside the copper is 0, so the cavity can have any shape and the charge inside the cavity can be anywhere. The outer charges will not be influenced by that. Since they are distributed uniformly, then the field outside this copper sphere will have spherical symmetry. And so we can find directly the field outside from Gauss's law, and it will be 1 over 4 pi epsilon naught Q over r squared along r hat. Now here is another question. Suppose now that we have a charge plus Q outside, nearby the copper sphere, with a cavity inside. So in equilibrium, what is the surface charge density on the interior of the hollow space? This time, if you answered A, that the surface charge density of the inner surface will be 0 everywhere, then you're correct. You can do the same Gaussian surface as we just did in the previous question, right? This time there is no charge inside the cavity, so the total charge on the inner surface has to be 0. It does not mean that it is 0 everywhere, only that the total is 0. Now, suppose that it is not 0 everywhere, that there is somewhere a negative surface charge and somewhere else a positive surface charge. Then the field inside the cavity will go from positive charge to negative charges, so it will not be 0 inside the cavity. And if it is not 0 inside the cavity, then draw a closed loop that goes inside the cavity along the field line and closes inside the copper region. We know again that in static, the integral of E dot dl on a closed loop has to be 0. We already have the electric field equal to 0 in the copper region. So to get 0 now, we need the field inside, E inside the cavity to be also 0. So for E inside the cavity to be 0, we must have no surface charges anywhere on the inner surface. Right? So the correct answer is A. The surface charge density on the interior surface is 0 everywhere. Now what is interesting with this example is that you see that what is inside the cavity is completely immune from the electric field outside the copper. The charge plus Q outside could be anywhere of any value, positive or negative. The field inside the cavity will be 0 no matter what. Right? And this is the concept behind Faraday enclosures. If you have a sensitive equipment, for example, that you want to protect from electromagnetic or electrostatic effects, you put it inside a metal box, right, inside the cavity. Right? Faraday cage bags are also used, for example, to protect phones, electronic keys from hacking and tracking, or unfortunately, they can also be used by shoplifters to bypass the security systems. A microwave oven is also a Faraday cage, this time to protect the outside and to keep the microwaves on the inside. Right? This is why there is a metal grid on the door of a microwave oven. And radio frequency shielding in MRI is also crucial. Usually the entire MRI room and the control units are in a Faraday cage. And a clear example of how this Faraday cage is a shield from for the inside cavities is the example of this aircraft. Right? On average, each aircraft is struck by lightning strikes once per year. And in that case, the passengers, the electronics, and the fuel tanks are all inside the Faraday cage. And the same thing for a car, right? The metallic frame of the car is protecting you in case of lightning. Right? It is not because the rubber tires are protecting you. In fact, motorcyclists, they are not protected from lightning strikes. Now let's move on to the force on the conductor. Right? To discuss this force, first we need to know the induced charge. And we will see that if you know either the electric field outside or the electrical potential outside, then you can find the surface charge of the conductor. Right? So how does it work? Remember the boundary conditions. For example, the boundary condition for the electric field tells you that the E field above the charged surface minus the E field below the surface is equal to sigma over epsilon naught n hat, where n hat is a normed vector perpendicular to the surface and in the direction from below to above. So since the E field inside the conductor is 0, then the field outside is simply sigma over epsilon naught n hat. Again, you see that the field outside is in a direction perpendicular to the surface of the conductor. And as we said before, that means the field lines terminate or start perpendicular to the surface of the conductor. So if you know E outside, then you can calculate sigma. And if instead you know the potential, then you can use the boundary condition for the potential that we saw last time. Remember that we saw that dV above dN minus dV below dN is equal to minus sigma over epsilon naught. So since the potential inside is constant, then its variation along n is 0. So we obtain another relation for sigma, sigma equal minus epsilon naught dV dN. So if you know the electric potential on the surface, or simply its variation outside in the direction perpendicular to the surface, right, the dV dN, then you know sigma. And with these two relations, you can determine the surface charge either from the E field or from the electric potential. Now that we know how to calculate the surface charge density, if we have an electric field and some charges, we also know that there will be a force on the surface, F equal QE. So if we write this per unit surface, F over a unit surface dA is equal to sigma E. But here we have a dilemma. Right? Let's say we have a surface charge and we consider a little patch of surface and we're trying to find the force on this patch. Which electric field should we take? Do we take the field above the patch? The field below the patch? Do we take the applied field? Do we take the field that is created from the surface? If we calculate the force on a small patch of a charged surface, do we consider the field created from the patch itself or the field from the rest of the surface? Now, the patch cannot exert a force on itself, right? Remember, a force is an interaction between one thing and another, so we will not consider the field from the patch itself. On the other hand, the field that is applied and the field from the rest of the surface charge should be considered. Now, the field that you have somewhere in space is the field from the patch plus the field from the other sources, right? So let's call this field E other. So if we want to consider the field, if we don't want to consider the field from the patch, we only want E other. Right? There is a trick to find E other. It is to write E other in terms of the field above and the field below. So the electric field above or below is the field from the patch plus E other. For E above, the field from the patch is pointing towards plus sigma n hat, and it is sigma over 2 epsilon naught n hat. For E below, the field from the patch is pointing in the opposite direction, so minus sigma over 2 epsilon naught n hat. In fact, the exact value of the field from the patch does not matter. All we need is that it is equal but in opposite direction above and below the patch. So this way, if you take the average, E above plus E below divided by 2, then you get E other. And so in the end, we can write the force per unit surface, F over dA, is equal to sigma times E above plus E below over 2. The force per unit surface has the unit of pressure, so it is called the electrostatic pressure. If you have a charged surface, there is an electrostatic pressure that applies to this surface, which is given by this formula. We will continue discussing this force, but before we do that, let's answer this question first. Consider the two situations, both with a very large or effectively infinite planes of charges, with the same uniform charge per unit area, sigma. Which situation has the larger electric field above the plane? Is it A, a plane of charges completely isolated in space? Is it B, a plane of charges on the surface of a conductor in equilibrium? Or is it the same in both cases? If you are stuck here, consider a Gaussian surface, for example, a box that has its top and bottom surfaces above and below a patch of the charged surface. If you answered B, then you're correct. Look at the isolated plane in A first. we have already done that before, but it's good to do it again. We know by symmetry that the electric field on both sides is the same, so the total flux of electric field going through our Gaussian surface is 2E times A, and the enclosed charge is sigma A. So Gauss's law gives us 2EA equal sigma A over epsilon naught. That gives us E equal sigma over 2 epsilon naught n hat. Nothing new, we have already done that before, but now let's compare with the case in B. Now the electric field at the bottom surface of the box, which is inside the conductor, is 0. But we have the same total charge inside the box. So that means that the field outside has to be twice larger. Right? We find E above equals sigma over epsilon naught n hat. That is the same result we got from using the boundary condition earlier in this video. And that is not surprising because using the Gaussian box is exactly how we derive the boundary condition. Right? So everything is consistent. Now that we got this reminder, let's come back to the force on a charged surface. We found that F over dA is sigma E above plus E below over 2. That's for any charged surface. But for the surface of a conductor, we can simplify this formula. As we just saw already twice in this video, the field outside is sigma over epsilon naught n hat. Right? And the field inside the conductor is 0. So the electrostatic pressure is sigma squared over 2 epsilon naught n hat. And if instead you want to write this in terms of E outside, you can replace sigma squared over epsilon naught squared by E outside squared. So you get that the electrostatic pressure is 1/2 epsilon naught E outside squared. Now before we conclude, I will mention two examples of the effect of electrostatic pressure. The first one is that since you can use an electric field to apply a force on a conductor, you can deform the surface and eventually you can even break it. Right? This method, for example, is used to measure the bending rigidity of a graphene membrane. And another example, which is funny, is this bubble launcher. Here, the membrane of this is the soap bubble, and it is a good enough conductor, so applying an electric field can apply a force on the bubble, and that's a pretty cool bubble launcher. So let's summarize what we learned. The most important result to remember is that the electric field inside the conductor is 0. From this, we also found that the charge density inside is 0 and the electric potential inside is uniform. We saw that there can be a surface charge density sigma and the field outside is equal to sigma over epsilon naught n hat. Right? This means that the field lines terminate or start perpendicular to the surface of a conductor. We also saw that sigma is equal to minus epsilon naught dV dN. And both of these can be useful to calculate the surface charge density sigma, if you know the electric field or if you know the electric potential. And finally, because we have surface charges and field, we saw that there is a force on a charged surface that can be calculated as sigma times E above plus E below over 2. And we saw how this can be simplified in the case of a conductor in terms of only sigma, if you know sigma, or in terms of the electric field outside, if you know the electric field outside. All right, so that's it for today, and see you soon.